Hello friends, welcome to this video, and in this video we are going to work upon the implementation of UNet 3 plus in the PyTorch framework. So let's get started. First of all, we're going to understand what is UNet 3 plus. So in simple term, we can say it is an advanced medical image segmentation architecture built upon UNet++, featuring full-scale skip connections, deep supervision, and a classification guided module for improved accuracy and reduce parameter. The model efficiently captures fine-grained details and coarse-grained semantic in the medical images, addressing issues like over-segmentation and false positive. Now, in the diagram below, you can see a direct comparison between UNet, UNet++, and UNet 3 plus. And here you can observe how the utilization of skip connection changes over time. So in the initial, that is UNet, it utilizes plain skip connections, while in the UNet++, it utilizes nested and dense skip connections, and also it uses deep supervision. While in our present, that is UNet 3 plus, it uses full scale skip connections and also deep supervision. Now about its architecture. So it utilizes two parts. First is the encoder, which is same as the UNet, while in the decoder it incorporates both smaller and same scale feature map from the encoder and large scale feature map from the decoder. So most of the new things which are added to this UNet 3 plus lies in the decoder part only, and here it says that it utilizes feature from both encoder and the decoder, and from encoder it utilizes both both kind of features, small, same scale, and you can even say large scale feature map. Okay, that's how it works. Next, its type. So we're going to implement it in three files, three separate. So first would be our normal deep supervision. Okay, sorry, first would be normal UNet 3 plus. In second, we're going to add deep supervision, and in the third part we're going to add classification guided module. So now let's move on to the normal UNet 3 plus. So here you can see the diagram. Just remove these deep supervision part, these four deep supervision blocks, and this architecture would become normal UNet 3 plus. So first of all, we are going to implement this part. So let's move on to the implementation part. First of all, we'll import the PyTorch framework. After that, we'll build the cone block. So our cone block basically consists of few layers, and these would be convolution layer, Bayes normalization, and the ReLU activation function. So here's the code for its implementation. So in its constructor, that is INIT function, it takes the number of input channel, then it gives you the number of output channel, and third is act, which is by default set to true. Next we have this layers list, and inside this list we add one layer, that is convolution layer, and we give its all its values. After that we check if act is true. So if the activation is true, act here basically refer to activation. If you want activation function, then we would append two more layers into this layers list. Here the first layer would be Bayes normalization layer, and second is the ReLU activation function. Now we have self.con, where we have these layers. Now in the forward function we execute it. Okay, so if the act is true, then it would have convolution layer, Bayes normalization, and ReLU. If act is false, it would only have the conv 2D layer only. So this is our basic building block for the entire architecture. Next we would have is the encoder block. So the encoder block is same as that of UNet. So inside the encoder block we would have con block. So basically two convolution layer, each followed by a Bayes normalization and a ReLU activation function. After that in P1 we have 2x2 max pooling layer, and inside the forward function we take the x as the input feature map, and we pass it via the conv layer first and then max pool layer. So we get two values. First is the x, that is the output of conv layer, and second is p, that is the output of pooling layer. Here x would basically act as skip connection for the decoder, and P would be the input for the next encoder block or the next block. Now we'll move on to its implementation, that is UNet 3 plus. What I'll try to do, it's better to copy paste things. It would be a bit slow if I write everything. I'll now explain. Okay, let me just do one thing. I'll put, okay, so we have this name of the class UNet 3 plus. In its constructor we say number of class equals to 1. Okay, so first of all, now we'll define our encoder. Encoder basically contain 4 encoder block. Okay, first is even. So number of input channel and number of output channel we have defined in every encoder block. So we have 4 encoder block. So if I move back to the diagram, here you can see it has 5 encoder block. It shows even, x1, x2, x3, x4, x5. So these are 5 encoder. So what I basically in my terminology, what I call these first 4, I call the part of encoder block, and this one which is between the encoder and the decoder, I call it bridge or the bottleneck. Usually I refer it this way only. So this is my terminology. Okay, so now we would have our bridge or the bottleneck layer. So this bottleneck layer only contain 2 cone block. Okay, it does not contain the max pool layer. Now if you observe, number of output feature channel is 64, 128, 256, 512 and 1024, and same thing we can observe in this diagram: 64, 128, 256, 512 and 1024. Same. Now in the decoder part, I'll make you understand why this value is 320. So till now we have defined all these layers. Now it's time we execute these layers, because in the init part we only define those layers, they don't run. Okay, now we have our forward function self. After that we say inputs. So this is basically the input feature map or the input image. So this image can be RGB or grayscale, but for now we are assuming it's an RGB image. But if it's a grayscale image, you can change its channel to 1. Okay, so now we have our encoder. So we'll run all these layers. So this is our encoder layers. So first of all, we call self.even, that is first encoder block, and we give it the input. So its output number of channel would be 64. Okay, here we have even and p1. If you observe here in encoder block, it give 2 values, x and p. So here if I say even, this is the output of the conv layer, and p1 refer to output of the pooling layer, that is max pool layer. Now p1 would act as the input for the e2. If you observe the e2, that is this encoder block, its number of input channel would be 64. That is the output number of channel of e1, and the output number of channel for e2 is 128. Same way from e2 we get 2 output, e2 and p2. In the same way we have 4 encoder block. Okay, and we have 8 number of output, that is e1, e2, e3, e4, p1, p2, p3, p4. Okay, now we have our bottleneck layer, that is e5. We also gonna refer it with the variable e. So here in this entire code, if I write e, this means it's a part of encoder block somehow. Okay, not somehow, it's a part of the encoder architecture only. So for decoder we usually add d in the variable name. So now the encoder part is done. Let's try to run it for once and check. So this is our main function. I am not in testing department, or I haven't run, but I think this is usually called unit testing. So let's run this testing. So first of all, we will have a variable for a tensor with the exact shape as our input image. So 8 would be batch size, 3 number of channel, and then the height and width of image. Let's say 256 by 256. So this is our image. We called our model. Okay, we don't need to give any variable here. We take number of classes and we only define it as 1. So if you want to change that, just change that according to you only. So now what I'll do, I say model and we give this input to here. Now it would run, but it won't print anything unless we say P5, E5, let's say. If it would have any error, it would not run, it will give you some error message on the terminal. So it does not have any error. And you guys in the shape of the E5, that is 8 batch size, number of channel 1024 as mentioned in this E5 layers. Okay, I need to move to the terminal, and here height and width to the feature map, they became 16. So I think they are decreased by a factor of 16, because if you multiply 16 by 16, it became 256 exactly. So now we'll move on to the decoder part, and that is where the novelty of UNet P+ lies. So first of all, we'll define all the layers first. So what I'll do, I'll copy paste every layer, and then we move on to its explanation. So we call it decoder 4. Okay, so first decoder which began, we call it decoder 4 as mentioned in the paper. See, it's called XD4. X, that is the tensor or the feature map, D refer to decoder, 4 is the fourth. So we move in the 4 3 2 1 like this, because it's easy to understand in this way. Now we have 5 layers here, and these 5 layers are basically because we have 5 encoder layer. 4 is from the encoder, 1 is from the bottleneck. So we call it E1 D4, E2 D4, E3 D4, like this we name them. So E1 D4 is basically a convolution, a con block is referring to the first feature map, that is E1, whose number of output channel are 64. We have put 64. Then for E2 we have number of input channel as 120. Same way, but here if you observe, number of output channel are always 64. So these are the 5 layer for the 5 feature map from the upper part of the network, that is encoder and the bottleneck. Now we have this last layer called D4. So what happened after these part, when we run those on block, so we have 5 different feature maps, each of exactly having same height and width. So we concatenate them, and when we concatenate them, so if you do 64 multiply 5, so 64 multiply 5 times, it became 320, and that is what is being referred here as 320. Okay, so now we have defined the layer. Now we'll try to execute them. This is also interesting how we execute them. Okay, so these are all the layers executed. Now we have decoder 4. Just remember, if you are implementing UNet here, so what should be the exact height and width of the output of decoder 4 here? If let's say the height and width are 16, then the output of D4 should be 32 by 32. Exactly that's what we are going to do here. So we need to make sure all the feature, that is E1, E2, E3, E4, E5 should have the height and width that is 32 by 32, that is equals to the height and width of feature map E4. So first of all, we have our feature map E1. So its size is 256 by 2556, and we need to make sure its height and width is equals to, that is 32 by 32. So we use a max pooling layer here with a kernel size of 8 and a stride of 8. So this way its height and width get decreased to 16, that is 32 by 32. So what I'll do, I'll print the shape of E1 D4 here for you. Hope there's no error here. So I'll comment out the rest of the part for now, just to show you. So this way you will easily understand. Now you can see 8 batch size, 64 number of channel, and 32 by 32 would be height and width of the feature map. Now what we'll do, we pass it via this con block, that is E1 D4. Now we'll print it out. You can see things are working fine. So in the same way, we have few more layers. So what I'll do, I'll uncomment them out right now. So for E2 we follow same max pool layer, but with a factor of 4. So here the feature map is decreased by a factor of 4, because the size of E2 is 128 by 128. And for E3, we again use max pool layer, but with a factor of 2, because the height and width of E3 is 64 by 64, and again it is followed by a cone block, that is E3rd D4. But for the E4, we don't have any max pool layer or any upsample layer because its height is exactly 32 by 32. That is what we require. So no extra layer is there, just a cone block. Next we have E5, whose height and width, if you remember, is 16 by 16. So here we cannot apply max pool. Here we need to apply upsampling. So here we use interpolation and use bilinear method to upsample the feature map by a factor of 2. So factor of 2 means 16 by 16 would become 32 by 32. And after that we have again a cone block here. So now the shape of all these layers is same, and let me print them here. And these are all the layers. I'll print their shape just to be sure that things are working fine, and it would make it easy for you and me to understand how we are going in this, how we are going with the implementation part. Their height and width should be same, and even their number of channels would be same. See, they all are same. So if they are not same, there would be a problem during the concatenation. Now we concatenate all these on the dimension 1, that is channel axis, and then after that it is again followed by a cone block. So this is the implementation of the decoder 4. That is how we do it. Now we'll move on to the decoder third. Again for decoder third we have same set of layers but with one small change, and which I'll tell you now. So this is decoder third. Again we would have E1, E2, E3, E4, E5, and again same number of input channel for E1, E2, E3. But for E4 now you observe there's a change, but for E5 it's same, that is 1024. And here you observe in the encoder the number of output channel for E4 is 512, but why we have changed it to 64? So now here's a twist. Now what I'll do, I hope you have understand these layers. It's a simple cone block. Now we'll move on to the layer part. I'll paste the code here, and then it would be easy for us to understand. Okay, so let's move slowly. First we'll go for E1. Now the height and width of D4 is 32 by 32. Now we need to make sure in decoder third the height and width of the feature map would be equal to the height and width of E third. So decoder third and E third, that is how we match them. So again we have max pool layer but by factor of 4. Then we have a cone block, again a max pool layer for E2 by a factor of 2. Then again a cone block. For E third their height and width are exactly same as required. So we don't need to make any change. But now we move on to the E4. So here we are using, instead of using E4, here we using the feature from the decoder 4, that is D4. That's why in this layer, this cone block, we say 64 instead of 512. Now if you go back to our slides, if you remember, it says it incorporate both smaller and some same scale feature from encoder and also large scale feature from decoder. So it says they use feature map from the decoder also, and that's what we are doing here. So instead of using E4, we are using feature map from D4. That's how we incorporate decoder level feature map in it. Okay, so for D4 we need to upsample it by factor of 2 and then a cone block. And same for the E5, we need to upsample it now by factor of 4 and then a cone block. So that's how it works. Again we concatenate and it followed by a layer, that is a cone block, and this finishes the decoder third. Same way, now we move on to the decoder 2. So what I'll do, I'll paste the layer of decoder 2 first. So we have decoder 2. Now you observe we have D3 and D4 again. So now I hope you understand now. Here we will also now we have two feature map from the decoder, that is for D3rd and D4th. Now let's paste the layers. Now I hope it is becoming easier for you to understand how this UNet 3+ works. So this is a simple version. Later we'll add deep supervision, classification guided modules in it. So again, now we need to make sure the feature map has a height and width equal to that of E2. So again, even pass via max pool with a factor of 2. Then a cone block. For E2, we have normal cone block. Now for E3, so what we do, we saying actually E1, E2, E3, E4, E5. But in between, we replace some encoder feature map with a decoder. Instead of E3, we are using D3. Again, feature map from the decoder third. We upsample it and it passes via the cone block. After that, we have E4, D2. Instead of E4, we are using D4, upscaling it by factor of 4 and then passing via the cone block. For E5, we are using E5 feature map only, upscaling it by a factor of 8 and then passing it via the cone block. And again, concatenating and passing via again a cone block, and D2 forms the output, the decoder 2. Now we have our last decoder block left, that is G1. Okay, just a bit of time. Yeah, I'll paste D1, that is decoder 1. Now here, all these layers have 64 by 64, that is 64 as input and 64 as output. Now we'll paste the layers. Now the feature map of the decoder 1 should be equal to that of the height and width even. See, now you observe, first the shape should be equal to E4, then E3, then E2, then E1. And so first is this E1, we pass it via the cone block, and after that we upsample each feature map and pass them via a cone block. So here you can see we are using D2 instead of E2, D3 instead of E3, D4 instead of E4, and for E5 we are using E5 only. So we upsample them so that their height and width are equal to 256 by 256. We concatenate them and pass via the D1 layer, again a cone block, and D1 form the output of the decoder 1. Now we need to have an output here. So for that we're going to have a convolution layer, simple convolution layer, no cone block or extra thing is required, because 64 is the output of D1, because here we are not doing deep supervision, so we only have one output, that is from the decoder 1. So the number of output channel is 64, and that is number of input channel for this output layer. 5.1 would be 64, and number of output channel would be equal to number of classes. Okay, now we'll implement it. We'll run this layer. So this is how it works. So we say y1 equals to model output. We're going to print the shape of y1, and that's the implementation of UNet 3+. Okay, we have some indentation in D3. Indentation is a problem. Line number 60. Okay, in line number 60. Okay, not here, the above. Okay, just a small thing, and I hope it runs successfully without any. So you can see the shape of the mask, that is 8, batch size 1 as the number of channel, because 1 is the number of class we have, then 256 by 256, that is height and width equal to that of input image. So this is the implementation of simple UNet 3+. I hope you understand it. So if you understand this part successfully, then you will be able to easily grasp over the next two implementation. Okay, in the next part we'll add deep supervision. So what I'll do, I'll copy paste this code and paste it here. Okay, so this is done now. Let me remove this part. Okay, so we'll move on to the deep supervision, and you already know the architecture. Same, just that for now we will have output from E5, that is the encoder 5 for the bottleneck layer, then decoder 4, decoder 3, decoder 2, and decoder 1. All that. Now let's do that part. So simply what we're gonna say, in the initializer part, that is this constructor we call it in the object oriented programming term. We say deep sup, that is deep supervision true. So by default its value is true. So we say self dot deep sup is equal to deep. So we have defined this value. So if we say it is false, deep supervision would not be applied. Now here in the output term, we need to apply deep supervision. So what I'm going to say is copy these layer and paste them here. Okay. So here we have layers. So if I say deep supervision equals to true, okay, it should be self. Okay, you can do anything. If deep supervision equals to true, then it defines 5 layer. For y1 refer to d1, y2 refer to d2, y3 refer to d3, y4 refer to d4, and y5 refer to e5. This e5. Its output number of channel is 1024. And if your deep supervision is not applied, its value is false, then it gonna have one output mask only, and that from d1. Now same thing we need to do here. It's really simple. It's not that difficult. So I'm gonna copy paste them. Okay, let me zoom out a bit and increase its size. Okay, now it's fine. So if self of deep supervision is true, then we're gonna have y1 d1 passes to y1 and we get y1 as our output. For the next, but first we pass them via the convolution layer, each of them d2, d3, d4, d5, and then we also upsample them to a specific size, that is 256 by 256. The size of feature map d2 is 128 by 128. So we pass them first via the conv layer, and after that we upsample them by a factor of 2, so that height and width became 256 by 256. And we do the same procedure for the rest, that is d3, d4 and e5, not d5, e5. So the size of y1, y2, y3, y4, y5 became equals to 256 by 256. And this procedure is done if deep supervision true, else we have same y1. Now let's run this program. So we call our model and give it the input, and we print the shape of all the 5, that is y1, y2, y3, y4, y5. Okay, now the file name need to change to second UNet plus with deep supervision. Now you can see we have 5 different outputs from 5 different blocks. First is from decoder 1, decoder 2, decoder 3, decoder 4 and encoder 5 for bottleneck layer. And you can see their height and width or their dimension are exactly same. So this is the deep supervision. So deep supervision usually helps if you are facing that your architecture is not improving, then this is one of the simple way to improve your performance. What this does is it facilitates better flow of gradients, because if you move on to this first part where deep supervision is not applied, so gradient would be calculated and they would be travel backward in this way only. So it is calculated at y1 only, but here it is calculated for 5 different outputs. Okay, so it facilitates better flow of information, better flow of gradient during back propagation. So that's why it helps. Now would be the third part where we would have both deep supervision and the classification guided module. So here we have our classification guided module. So here we have the decoder 1, decoder 2, decoder 3, decoder 4 and the encoder 5 or the bottleneck layer. And with deep supervision, each of them predict a mask. Okay, now it has some value. Now what we do, we take the feature map from the encoder 5 and we pass them via dropout, 1 by 1 con, adaptive max pool, then sigmoid. So in the 1 by 1 conv layer, we give it 2 classes. Okay, and then we pass them via the argmax. So this they would have some value. Okay, so if in it has 2 value in argmax, either it would give you value as 0 or as 1. Now let us imagine how it would work and why they use it. I'll tell you. Let's say in case of any image which does not contain any organ, so it should not have any mask, and by default if it give you mask something like this, like here the white region indicate it has some organ, the mask are saying, but in the image it does not have any organ. We know it. Now how to tackle this problem? So if the value of this argmax is 0, what we do, we multiply this mask with this output of this classification part. So if anything multiply with 0, it became 0. Now here you can see in the mask, so the output of this multiplication would be blank mask, everything would be 0. So in this way it help to facilitate the training. It would help in class imbalance also, because in some data set organs would not be present. So this classification module would help you to tell whether organ is present or not. If organ is not present, then it would directly wipe out any information about the location of the tumor or any specific organ which you want to segment. Now in the next case, if the value of this classification module is 1, now let's say our image have an organ and these masks indicate an organ. So what we do, we multiply these masks with the value 1. So there would not be any change. If you multiply anything with 1, it would become 1 only. Okay, so that's how it helps. Now here you need to remember that the value 0 and 1 have specific meaning. 0 would always stick with no organ, 1 would always stick with having organ, because if you interchange them, their meaning would be completely changed. Okay, so just remember that in this case. Now let's move on to this training part. Now what I'll do, I'll paste the code here and let's, okay, what I'll do, so first of all we have this classification guided module layer after E5. So this is our classification layer. First drop out of 0.5, then a 1 by 1 conv layer with 2 as the output number of channel, then a adaptive max pool layer and a sigmoid as the output, same what is mentioned here in the original paper. Now we'll execute these layer. So what we do, so first of all we run those layer, those classification, and we have the result of the sigmoid layer, because that is the last layer. So let me do one thing, let me remove this statement. So what I'll do, I'll print the output of this CLS for you so that you can see what it gives. And even I get to know, okay, these are some large values. Okay, let's just print this shape. And also let's do one thing, instead of giving 8 images, a batch of 8, let's give them 1, so it would be easier for us to understand. Okay, sorry, these are here. So we print CLS also and its shape, because both shape and its value are important. So these are the two value, first is 81, second is 80. So in this random image, it's saying this value is greater, it's saying it has no organ, and its shape is something like this. So now what we do, we pass it via the argmax on this channel dimension with the value of 1. Now we print the shape of it and let's see how the output looks like. So this is how it look like. Let's see its value also. Value is also important. Let's print that also. Shape and both value are important. Here you can see its value is 0. This is the shape. Now we need to make it a four-dimensional shape. That is 4 dimension. That is batch size, channel, and that is one value, then height and width. Because we need to multiply this value. So what we do, we're going to reshape it via the view function. So we say cls.view. This is the batch size. Then we add this one extra dimension. Then this is the height and width of the feature map. For now, let's go back to 8. And where are we? Okay, now I'll show the shape before and after view so that you can easily understand. You can see this is how the shape changes, and this shape can be easily multiplied with the output of our this as segmentation part, that is a decoder part. Now the next part is really simple. What we need to do, we need to multiply this CLS, that is output of classification part, with our output of this decoder. Just that simple thing, and you are done with this. Just that, nothing else you need to do. And this is your classification guided module. Also, now you have one more extra output. If you remember, classification also need to be trained. Okay, so just don't forget that also. Okay, this also need to be trained. So what we do, let's make one small change here. We can copy this. We can say CLS output to CLS, because this would be the output of this layer. Okay, so now one more thing you can add here, and this would only work if deep supervision is true, as according to paper. This only is shown with the this. Maybe you can also implement it without deep supervision also, that would also work. Just that multiply it with this one, multiply it here and add this as the output. Just that it would work. But let's just go according to the paper only. Now CLS, that is the output of this layer, CLS code shape. Now this is the complete implementation of UNet 3+ with all its block variants and every other thing. I hope you got it now, and you can pre-process this part, so it would work during the training. Okay, so this is the complete implementation of UNet 3+ in the PyTorch framework. I hope you learned something from this video, and maybe you can use it in your research paper or some project. So that's all for this video. Please make sure you like the video, share it with your friend, and do subscribe the channel. So thank you and have a nice